Before we start talking about the energy flow through ecosystems, I want to talk a little bit about the perspective that a lot of people have toward ecosystems. Um, you hear a lot in sort of the popular media and among people who aren't scientists about things like the balance of nature and the harmony of nature. We have to be a little bit careful when we're thinking about ecosystems, when we're thinking about nature, because it's very easy for us to project what we believe and feel or want or fear onto nature itself. So, for example, um, a lot of people feel that the way that human beings do things is really kind of messed up. And they look to nature as an alternative, something that's more beautiful, more perfect, and so forth. It used to be actually that a lot of people saw nature as a thing of dread. It was uncontrollable, unpredictable, and scary. Um, both of these attitudes can be problematic. I'm not going to say that finding something emotional or spiritual in nature is wrong. I don't think it is. I find very meaningful spiritual and emotional experiences in nature. But we have to be careful that having those emotions or perspectives in ourselves doesn't blind us to what nature is actually doing kind of on its own terms. Um, we may like to think that nature is in harmony, that there's a balance in nature, but it turns out that concepts like that, though they may have beauty and value to us personally, they don't turn out to be useful in terms of predicting what a natural system, an ecosystem is going to do. They don't turn out to have a whole lot of value in explaining what it does. And to me, it always seems a little bit disrespectful to project our values and desires and feelings onto organisms that legitimately have their own agenda and are doing their own thing. So again, I don't want to say that these sort of that emotional or mystical or spiritual ideas are wrong, but they don't have a lot of usefulness in science. And so when we're kind of in science world, we tend to set those aside. We tend to think about science over here and kind of the emotional stuff over there. Um, I would encourage you to take that perspective. Why am I bringing this up now? Well, because as we start to talk about ecosystems, they're an area where people tend to have a lot of these ideas. They tend to have a lot of ideas that the system is harmonious and in balance, and it's natural and good and stable in a way that other things aren't. And often this actually isn't the case. It turns out that it's more useful from a scientific perspective, from, if you're trying to predict or explain things, to think about all the little parts are sort of, they're out for themselves. Basically, all the species are, they're adapted to survive and reproduce as well as they can. Matter does what matter does. Energy does what energy does. And the picture, the whole picture that emerges, it isn't really guided or controlled in the way we usually think of things as being guided or controlled. It just sort of comes out the way that it does. Another thing I'd like to point out is that when we talk about the balance of nature, often we're overlooking the fact that ecosystems do sort of vary wildly sometimes from one point to another. There are population crashes, there are population booms, there are big changes even when human beings aren't tinkering with them. So let's keep that in mind as we think about these systems. Okay, I'm going to get off my soapbox and start talking about the way that energy moves through ecosystems. Energy is really important to living things. And all of the energy in the ecosystems that you're familiar with ultimately comes from the sun. That means that it has to get into a living community by being captured by what are called producers or autotrophs. The word autotroph means it feeds itself. And that's what plants and other photosynthetic organisms do. They capture light energy and they store it in the chemical bonds of food. That's basically what food is. Food has nutrients, but mostly it contains high energy chemical compounds that your body can extract the energy from. In photosynthesis, what happens is that photosynthesis takes the light energy and stores in the bonds of a chemical compound called glucose. And all organisms burn high energy chemicals, and we're going to be looking only at glucose in this class. They all burn high energy chemicals to get out the energy they need in order to maintain their cells, in order to survive, in order to reproduce. When I say all organisms, I mean plants too. So plants do burn the fuel that they make. Okay, some students are confused. They think that plants only do photosynthesis and that it's only animals and fungi, for example, that do what's called cellular respiration. Cellular respiration is this burning that I'm talking about here that gets the energy back out of the glucose. That's incorrect. Plants do it too. They have to use their energy stores in order to stay alive, just like we need to use energy in order to stay alive. The big difference is that consumers, or heterotrophs as they're called, the things that eat others, they only get energy if they take high energy chemical compounds from another organism. Okay, they can be taking high energy chemical compounds from a plant, they can be taking it from another animal, but ultimately the energy in those compounds came from some photosynthetic organism that built those compounds using solar energy. Okay, so what happens again is energy enters the system through photosynthesis, and then it travels from producer to consumer in the form of energy-rich chemical compounds containing carbon. Glucose is the main energy carrier that we tend to think of. And that carbon-containing compound, glucose, can be made into a lot of other compounds. You'll notice that this compound here, just like glucose, is mostly carbon and hydrogen with some oxygens thrown in. This fat molecule stores a lot of energy, but it's made out of glucoses. So these molecules get made into this. The rest of the stuff in an organism's body is also mostly made from the carbons that originally came from glucose. So a plant, for example, it makes proteins, okay, which look like this. Again, carbon, hydrogen, little oxygen. Wood is this incredibly complex chemical compound, but all of this is hydrocarbons, carbon and hydrogen. Those all came from glucose. Starch is an energy-containing compound, again, made from glucose. Cellulose, nucleic acids, basically everything in a plant. All biomass originally started out as glucose, the product of photosynthesis. What happens to those high-energy compounds after the plants make them? Well, let's take a look. Let's suppose the plant dies and you've got a log that's lying there in the forest. This is called the lowest trophic level in a food chain. A fungus might come along and consume some of the high-energy compounds in that log, so it obtains the energy that used to be in that log. That fungus might be eaten by an animal, like this millipede. And that animal might in turn be eaten by the salamander. So you've got these high-energy compounds moving up from one organism to the next. And they might change form, they might change, their molecular form, but the energy that's in the chemical bonds down here ultimately gets transferred up to this salamander, or at least some of it does. The salamander is called the highest trophic level, and altogether this is called a food chain. The energy travels up the food chain and not generally back down. If you put a handful of these food chains together, you get something that's much more realistic. This is a food web, and in reality, this is what you get. You get all of these more complex interactions woven together. In fact, real food webs are insanely complicated in many cases. We're not going to be thinking about anything like this, but this is really how complicated things get when you're talking about who eats who in nature. Okay, what happens to that energy as it moves through the ecosystem? Well, let's start with the sun. The sun actually pours a tremendous amount of energy onto the Earth. There's 1,000,000 calories in a square meter. That's about 3 feet on a side. That's a square about 3 feet on a side. Every year, 1,000,000 calories drop down in the form of sunlight onto that area. A minuscule amount of that actually gets captured by living plants. And most of the energy that's captured by living plants gets used up or lost. So it's converted into kinetic energy that's used to move molecules around. That's what keeps the plant alive. Or it's just lost as heat. There's a certain amount of inefficiency, and even plants, when they do stuff, they generate heat as a waste product, essentially. Once that energy is used for, basically it's used to move things around, or it's radiated as heat, it's totally lost. It can't be captured and used by any other living organism. 45% of the energy that plants or other producers take in gets used to make bigger plants or to reproduce. In other words, it makes more plant biomass. Of that 45%, something like a quarter gets eaten by consumers. Okay, most of it, about 3/4, the plant material just dies and goes into the decomposer food web. So if you are an organism that does not eat anything in the decomposer food web, only about 10% of the energy that's captured from photosynthesis, or that's captured in photosynthesis, is making its way to you in the first place. A tremendous amount of that energy is lost. Chipmunks in particular are warm-blooded, like all mammals and birds, and they burn a tremendous amount of energy keeping themselves alive and keeping themselves warm. 80% of the energy the chipmunk takes is just lost as kinetic energy or as heat. There's a lot of energy in the food that's never assimilated. It's never taken into the body, about 20%. Only between 1 and 2% of the chipmunk's energy is made into, goes into making more chipmunk. What this means is that at every step in the at every step in the food web, most of the energy is lost. Only about 10% of the energy in general, 10 to 20% of the energy makes it from one level to the next. And so you get what's called a trophic pyramid. What the trophic pyramid means is when you're at the lowest trophic level, there's a certain amount of energy available. There's much less up at the next trophic level, about 20 or 1/5 to 1/10. Even less at the next level, and so on. Until when you get up around the 4th trophic level or the 5th, there's only a tiny amount of energy that's reaching this trophic level. Now, it takes the same number of calories to build a pound of any kind of organism, basically. So it takes, let's say, if you only get 20% of the energy moving up from these primary producers to these primary consumers, that means you can only build 20% of the biomass at this trophic level. If the efficiency of energy transfer is only 15%, that means that the biomass here can only be about 15% of the biomass here. The result of this is something that you're probably pretty familiar with. If you go out into any ecosystem in the world, whether it's a forest or a swamp or even an ocean, what you'll see is mostly primary producers. You're going to see very few consumers. You're going to see relatively few organisms that eat plant matter. And in terms of top predators, you'll hardly ever see them at all. They must be very rare because there simply isn't enough energy making it up through the food chain to support very many of them.